Morning students, myself Dr. S. Devikala, Associate Professor in the Department of Chemistry, SRM Institute of Science and Technology. In today's class, let us see in detail about macromolecules. The term macromolecules means it nothing but polymers. The word poly means many, meros means units. So polymer means several units combined to form a single giant molecule that is called polymer. So the word polymer is derived from the Greek word poly and meros, meaning many and parts. So the word poly means many, meros means units or parts. So polymer, a substance composed of molecules that have long sequences of one or more species of atoms or groups of atoms linked to each other by covalent bonds. For example, in this equation, ethylene polymerized to give polythene. This small n is nothing but the repeating unit. On the reactant side, you have to write it on the left hand side, whereas here, after the bracket, you have to enclose with n. So before 1920, the polymer was considered as physically associated aggregate only, but in 1920, Hermann Schrödinger said that polymers are composed of very large molecules containing long sequences of simple units linked together by covalent bonds. So in 1920, Schrödinger introduced the word macromolecule to describe polymer. He got Nobel Prize in 1953. Sometimes polymer and macromolecules are used interchangeably. So macromolecules are materials with large sizes and high molecular weights, while polymers also have large sizes and high molecular weights but consist of repeating molecules in their chemical structure. So polymer is formed by macromolecule. One of the macromolecule structure is given over here. It is called as lignin. It is macromolecule but not polymer. All polymers are macromolecules, but all macromolecules are not polymers. So polymers, macromolecules, but macromolecules, they need not be polymer. Certain terms we have to define here: monomer, polymerization, and degree of polymerization. The starting material is called as monomer. Degree of polymerization, it depends on the number of repeating units present in the uh, polymer, whereas polymerization, the process, overall process is called as polymerization. Let us see one by one. First term, monomer. The repeating unit by which a polymer or a macromolecule is formed is called monomer. The process through which monomers link together and formed a polymer is known as polymerization. The number of repeating units in a polymer is known as degree of polymerization, that is denoted by small n. The most basic requirement for polymerization is that each molecule of monomer must be capable of being linked to at least two or more other molecules of monomer by chemical reaction. That is, monomers must have functionality of two, or it may be more than two. It may be bifunctional, trifunctional, and so on. So the next term is functionality. So functionality of a monomer is defined as the number of chain links it can give rise to, or it is the number of bonding sites or reactive sites present in the monomer, that is called as functionality. So the polymers formed by chain polymerization of olefinic monomer, that is ethylene and its derivatives, contain single C double bond C bond contain C double bond C double bond. These monomers have a functionality of two because each carbon-carbon double bond gives rise to two chain links. So ethylene polymerized to give polythene. So this C double bond C. This carbon bond can be broken. By cleaving this, we are able to add two groups, so it is bifunctional. If your monomer has a functionality greater than 2, then this will lead to the formation of branches and possibly the formation of network of polymer depending on the particular polymerization. So next one is the classification of polymers. Polymers can be classified based on the origin or source, based on skeletal structure, based on molecular forces or structures. Let us see one by one. First one, based on source and origin, based on the occurrence or origin. Natural polymer, semi-synthetic, unsynthetic. Natural, as we know, naturally occurring. Example, protein, starch. Whereas semi-synthetic, cellulose acetate, nitrocellulose, etc. That is, these are prepared by chemical modification of natural polymer. Whereas natural, they are found in plants and animals. Example, protein, cellulose, starch, some resins and rubber. Whereas synthetic means man-made, so directly synthesized from monomers by chemical reaction. These man-made polymers are extensively used in daily life as well as in industry. Several polymers are there. Then classification based on skeletal structure, how the carbon chains are oriented in space, linear, branched, cyclic, network or cross-linked. So polythene linear, polyethelenamine, cyclodextrin and bakelite cross-linked, that is three-dimensional structure. Then based on molecular forces or structure, or you can call it as based on application also. So polymers based on thermoplastics. Under thermoplastic you have crystalline and amorphous, elastomer, rubbery material, and thermosets, thermosetting plastics. So here thermoplastics, they are often called plastics, either linear or branched polymers which become liquid upon the application of heat, can be molded or it can be remolded in any shape. They have both melting temperature and glass transition temperature. Melting temperature Tm, glass transition temperature Tg. For example, polyethylene, polypropylene, nylon, polystyrene, etc. Everything it comes under thermo. Thermo in the sense it can be remolded. Whereas elastomers, generally they are cross-linked rubbery polymers that can be stretched easily to high extension and rapidly recover their original dimensions when the applied stress is released. So cross-linking density is less. These degrade rather than become fluid upon the application of heat. For example, butyl rubber, polyisobutylene, polysilicones, polys polysiloxanes are nothing but silicone rubber, and polyurethane, spandex, etc. And then the third category, thermosets. Thermosets mean thermosetting polymers. They are normally rigid materials and are network polymers in which chain motion is greatly restricted by a high degree of cross-linking. Generally, they degrade rather than become fluid upon the application of heat. For example, vulcanized rubber, bakelite, epoxy resin, etc. Generally, they are insoluble. So the next one, with respect to stereochemistry of polymerization. Here only the skeletal structure and the chemical composition of the repeating units. Also the molecular microstructure strongly influences the properties of a polymer. So variation in the geometric and configurational arrangements of the atoms in the repeat unit and the distribution of these different spatial arrangements for the repeating units along the chain are of particular importance. Ziegler-Natta used the term tacticity in order to describe the different possible structure. Tacticity, it is nothing but the orientation of groups or functional groups with respect to the main chain. How the groups are oriented, that is directed in space. Based on that, you have three types: isotactic, syndriotactic, and atactic or atactic. So a pentant group or side group is a group of atoms attached to a backbone chain of a long molecule, usually a polymer. So based on tacticity, we can classify polymers into three types: isotactic polymers, syndiotactic, and atactic. If the groups are on the same side, then it is iso means same, no? So isotactic. Whereas syndiotactic means if the groups are in alternating position, then it is syndiotactic. Atactic or atactic means random position. So in isotactic polymer, all the repeat units have the same configuration. Whereas in syndiotactic, they are alternate from one repeat unit, that is alternating position. Whereas irregular arrangement means it is atactic. For isotactic polymer, one example is natural rubber. For syndiotactic, artificial, that is synthetic rubber. For atactic or atactic, example is polypropylene. Then based on the presence of elements, whether carbon is there, hydrogen is there, nitrogen is there, oxygen, accordingly the polymers are classified as homopolymer and copolymer. Homo means same. So the polymers are made up with one species of monomer itself means then it is homopolymer. So in case of ethylene, throughout you have carbon, carbon, carbon units only. Whereas in case of copolymer, it will have more than one monomer. Then it is called as copolymer. So polymer formed by two different monomer means it is copolymer. For example, polyhexamethylene adipamide, it is nothing but nylon 6,6. Let us move on to the types of polymerization reaction. You have addition, condensation, and copolymers. Let us see one by one. So first one, addition polymerization. In case of addition, mere addition only, these are the exact multiple of the monomer. So suppose if you are starting with n as 1000 means you will end up with 1000 only. So addition polymerization, it yields polymers with repeat units having identical molecular formula to those of the monomer from which they are formed. That's what I told you now. Then in condensation, these are polymers with repeat units having fewer atoms than they are present in the monomer and involve elimination of small molecule. Apart from having fewer atoms, elimination of molecules like H2O, HCl, NH3 that will occur. That such type of polymerization is known as condensation polymerization. So this addition, it is also called as chain growth polymerization, whereas condensation is also termed as step growth polymerization. So in chain growth polymerization, in which a polymer chain grows only by reaction of monomer with a reactive end group on the growing chain, and usually it requires an initial reaction between the monomer and an initiator to start the growth of the chain. So it is called as chain growth, mere addition only. Already I told you exact multiple of the monomer. Whereas in step growth polymerization, in which the polymer chain grows stepwise by reaction that can occur between any two molecular species. Any two molecular species in the sense any two monomer. Apart from that, removal of molecules like NH3, HCl or H2O. So it is step growth. So in this slide, you can see the differences between addition and condensation. So it involves monomer contain unsaturated group. Here it involves monomer that need not be unsaturated. It may be bifunctional or tri. Here no elimination of molecule. Here elimination of molecules. Here formed by this method have identical number of atoms compared to the monomer, whereas here lesser number of atoms. It can be described by chain growth, whereas it can be described by step growth. Formed products are called addition or chain polymers. Here it is called as condensation. Then the examples are, some correction and mistake is here, polyethylene from ethylene, nylon 6 and nylon 66 from adipic acid and hexamethylene diamine. Let us see some of the examples of addition polymers, their preparation properties and uses. Polypropylene, polystyrene, PVC, that is polyvinyl chloride and Teflon. So in addition polymers, let us see first one, polypropylene. So the starting material is propylene. So propylene polymerized to give polypropylene. N is missing over here. So polypropylene can be prepared by using propylene in presence of Ziegler-Natta catalyst. That is Ziegler-Natta catalyst, well known to us, organometallic halide with transition metal halide. Some of the properties are listed over here. Just you can have a glance. Isotactic, crystalline. Uses, it includes polypropylene can be used for making ropes, carpets, blankets and so on. So the structure of Ziegler-Natta catalyst is given over here. The next one is polyvinyl chloride, that is PVC. Acetylene plus HCl, you will get vinyl chloride. Then vinyl chloride on polymerization, you will get polyvinyl chloride. Some of the properties listed here: colorless, odorless, chemically inert, and so on. Some of the uses are: it is used for water hoses, toys, raincoats, and so on. And the next one is polystyrene. So here styrene polymerized to give polystyrene. Temperature mentioned over here 60 degree centigrade. Some of its properties are hard, transparent. It is widely used as plastic. It is non-biodegradable. So this comes under synthetic. So the medical uses, it is used for sterilizing test tubes, diagnostic components, and so on. And it is used as thermal insulation in refrigerator, freezers, etc. It is used in housing in all IT equipment such as television, computer, etc. The next one is polytetrafluoroethylene, that is Teflon. The starting material is tetrafluoroethylene. In ethylene, if you replace all the 4 hydrogen atom by fluorine, then you will get tetrafluoroethylene. Tetrafluoroethylene polymerized to give polytetrafluoroethylene. Some of its properties, let us see. It has low coefficient of friction, good mechanical and electrical properties. Some of its uses it includes: it is used in insulating motor, cables, wires, etc. The main application is non-stick cookware. Let us see some of the examples of condensation polymer: nylon, polyethylene terephthalate, polyurethane, and synthetic rubber. Under synthetic rubber, either you can have bunion or bunias. So here nylon 66, 66, 6, and several equations are here, and some of its properties along with the equation. Nylon 6,10, it has good resistance to most solvents, and main uses: it is used in precision parts, filaments, and brushes. Whereas nylon 6 prepared from the starting material is caprolactam. Caprolactam polymerized to give nylon 6. It is used in the synthesis of artificial fiber, fishnet, and then in making parachutes, airbags, etc. And then the next condensation polymer is polyethylene terephthalate. So here polyethylene terephthalate, in short form you can call it as PET. It is a condensation polymer of ethylene glycol and terephthalic acid. The temperature maintained is 80 to 300 degree using an acid catalyst. Some of its properties include crystal clear polymer, purity, good barrier, recyclable, good resistance power. It is some of its application include shopping bags, water bottle, microwave containers, and so on. Polyurethane, again one of the well-known condensation polymer only. So the equation is given over here. Some of its property includes: it is soft, spongy, known as U-form. It has low thermal conductivity, and so on. Whereas it is used as an insulating material in refrigerator. Due to its spongy nature, it is used for making pillows and mattresses also. So polyurethane, generally it is represented like this: Pu or PUR is an organic polymer prepared by the addition reaction. Most polyurethanes do not melt upon heating, therefore it can be classified as thermosetting. The next one is rubber. You have both natural rubber as well as synthetic rubber. For natural rubber, the starting material is isoprene units. For synthetic rubber, you have to start from neoprene units. Then the concept of vulcanization of rubber. Vulcanization of rubber is nothing but it is the process of heating rubber with sulfur in presence of a catalyst at a temperature of 80 to 100 degrees centigrade. That is called as vulcanization. So during 1839, Charles Wood Charles Goodyear developed the method of vulcanization of rubber, by which the properties of natural rubber can be improved to a larger extent. So vulcanization is a process which is essentially compounding rubber with different chemicals like sulfur, hydrogen sulfide, benzoyl chloride, etc. So this method is basically heating raw rubber with sulfur at 100 degree to 140 degree. When the sulfur enters into the double bonds of rubber, forming cross links between the chains, and this gives the structure and toughness. The toughness or the stiffness of vulcanization, it depends on the amount of sulfur added. For flexible tire rubber, sulfur content is from 3 to 5%, whereas for tougher variety like ebonite, sulfur content should be 32%. Ebonite is so tough so that it can be machined, and it has very good electrical and insulation properties. So in this table you can see the property: elasticity, tensile strength, chemical resistance, resilience, durability, quality, etc. with respect to raw rubber versus vulcanized rubber. So raw rubber elasticity very high, whereas in case of processed rubber, vulcanized rubber, it is low. Similarly, chemical resistance is very poor in case of raw rubber, whereas it is once it is processed, it is high. Then water absorption tendency, it is high in case of raw rubber, whereas it is low in case of vulcanized rubber. Then resilience, good in case of raw and much better in case of vulcanized rubber. There are several synthetic rubber. So the first one is GRS or Buna S. Here S stands for styrene, Buna stands for butadiene. So butadiene plus styrene copolymerized to give styrene butadiene rubber. Some of the properties includes it possesses high resilience and good and tough mechanical properties. SBR rubber uses it includes insulating wires and cables, adhesives, and lining for vessels. GRA or Buna N. Here again Buna means it is butadiene, N means acrylonitrile. So butadiene plus acrylonitrile copolymerized to give Buna N, one of the synthetic rubber only. So the properties: resistance to heat, sunlight, acids, oils, etc. Whereas its application, main application, it is used in making automobile parts, aircrafts, and also it is used for making conveyor belts, adhesives, and oil resistant foams. And then third one, GRM, or it is also called as neoprene. It is made by the polymerization of chloroprene or alpha chlorinated butadiene. One of the hydrogen in butadiene has been replaced by chlorine, means it is chloroprene. So this chloroprene polymerized to give GRM or neoprene. Its properties includes marked resistance to temperature, atmosphere changes to atmospheric changes, and then resistant towards oils. And it is also used for making conveyor belts, adhesive gaskets, and so on. The next one is formation of terlin or Decron. Commercial name is Decron. So how terlin is prepared means by treating ethylene glycol with terephthalic acid. H2O molecules are said to be removed, eliminated. So the product formed is terlin or Decron. The next one, conductive polymers. Why they are conductive, how they are conductive means due to the presence of 5 electrons present in the. So there are several conducting polymers: intrinsically conducting polymer and extrinsically conducting polymer. So here the conduction is due to extensive conjugation in the backbone in the polymer chain. So conjugated conducting and doped conducting. Conjugated conducting polymers means polymers contain alternate double bond. That is called conjugation. Compounds containing alternate carbon-carbon double bond is called as conjugation. Whereas doping by adding some dopants. Whereas in case of extrinsically conducting polymer, polymers with conducting elements, that is polymer matrix along with the conducting fiber, On the other hand, polymers with conducting blend, non-conducting polymer blended with conducting polymer. So the basic classification, you have two types of conducting polymers, intrinsic conducting polymer and extrinsic conducting polymers. So some of the conjugated polymers list have been given here: polypyrrole, polyaniline, polythiophene, polyacetylene, polyparaphenylene, polyphenylvinylidene, polyfluorine, and then pedot. So one of the well-known conducting polymer is polyacetylene. This is the equation: acetylene polymerized to give polyacetylene in presence of Ziegler-Natta catalyst. So acetylene on passing over Ziegler-Natta catalyst at room temperature, it forms polyacetylene. So polyacetylene is the first example of synthetic conducting polymer. So you have both cis polyacetylene and trans polyacetylene. Some of the applications of trans polyacetylene, it includes: it is used as lightweight electrodes for rechargeable batteries, conducting films and powders, corrosion resistant paints. It is used in gas sensor, anti-static substances for photographic films, electromagnetic shielding for computers, smart windows, even in solar cells, LEDs, and mobile and television displays. So there are doping, I said, two types, P and N. So the polymers which have conjugation in the backbone, when treated with electron deficient species, that is, electron deficient means Lewis acid, for example, FeCl3 or iodine vapor or CCl4, etc. So polymer plus Lewis acid, you will get polymer doped polymer, that is oxidation of polymer. So polyacetylene general representation CHX. So removal of one electron from the pi backbone of conjugated polymer forms a radical cation, that is, the radical cation is called as polaron, which on losing another electron, it forms bipolaron. The delocalization of positive charges, it causes electrical conduction. So the next one, N doping. So here Lewis base, in P doping we have seen Lewis acids, that is electron deficient, whereas here Lewis base electron rich species are treated with polymers having conjugation. Due to reduction of the polymer, negative charge developed. So polymer plus Lewis base N doped polymer. So the last conducting polymer is P3HT. It is nothing but poly 3-ethyl thiophene. The structure of 3-ethyl thiophene. This is the structure of 3-ethyl thiophene when it is treated with FeCl3. The reaction is oxidative coupling in presence of nitrogen gas and CHCl3, that is chloroform. The product formed is poly 3HT. It is nothing but poly 3-ethyl thiophene. Some of its properties: it is semi-crystalline, and then the glass transition temperature is 12 degrees centigrade. It has high tensile modulus of 200 megapascal to 1 gigapascal. And then some of its application includes: it is used in optoelectronic and electronic fields, mainly in storage devices like solar cells. So in today's class, we have seen what are macromolecules, how they are defined, their classification, and then type of polymerization, and then what is the difference between addition and condensation polymerization, preparation properties and applications of some addition polymers as well as condensation polymers. Apart from that, we discussed in detail about the conducting polymers and its classification with suitable examples. So with that, I'll conclude today's class. Thank you.